where he's also part of the ChiData Center, the Data System Research Group. He was a postdoctoral research fellow at MIT before, and he obtained his PhD from Imperial College of London. And his main research area is about economics and value of data. So, well,
great. First of all, thanks so much for inviting me here. I think I've had a great time the last couple of days. Really good research, really good set of ideas. So I'm hoping that today I will be telling you a little bit about something that maybe sounds new, and I'll give the context first by saying that my research goal, the research goal that my group is pursuing at the University of Chicago, is on understanding how to design well-functioning data markets, and a pre-requirement to get there is to understand what's the value of data. So these questions that sound very abstract, I'll try to make them just a notch more concrete in a second. I'll comment, or I'll say that the methodology that I use for doing research is to actually build systems. I care a lot about building software that I can deploy in the wild with the hope that I will be able to use those systems to measure metrics that are interesting or that are important to me. And what that means is that a lot of the work that I publish is to conferences like SIGMOD, VLDB, and ICDE. So it's been great to hear sort of the kinds of questions that this audience ask and the kind of research that you are all doing. So let me give you just a notch more concrete idea of the research agenda, and then I'll just jump right on the technical talk. And so I say that I define a data market as any environment where agents exchange data. And those are the kinds of environments that I'm precisely interested in understanding how we can design better. I say that the value of data arises from data markets because I think it's precisely in those exchanges between agents, when we move data from one point to another, that value can appear. Now, that definition doesn't, I hope, shouldn't be too surprising if you think about cases where the data is exchanged explicitly. Like if you think of marketplaces, like these online websites where you can list a set of data sets that are for sale, you can go pay some money and obtain them, that's pretty clearly a kind of data market, right? Like data is what's being sold. Data sets are what's being sold. And the same might be true for mergers and acquisitions when companies have to set up a virtual room to list the assets that they have so that they can make a case perhaps for their valuation to be higher, and so on. And there are of course, lots of other what I also call data markets that are maybe less obvious to think of them as such. Like when we talk to Google or Netflix or Twitter, it's essentially a barter market in the sense that we are giving them our data in exchange for the service that they offer, right? So I think of that as a data market as well. And I like this idea of thinking about data market under that definition because it puts this lens on all these different scenarios that I think opens up opportunities for us to think, well, so what are the areas where maybe we haven't thought about the agent as one of the key components of the scenario, and what are the implications of that? And of course, the background for this talk is that many of the existing data markets do not work very well, and I'll be focusing today on data marketplaces. And so these are, as I mentioned, those that you can go online right now. You can go to Amazon Data Marketplace or Snowflake, or Narrative, and you're going to see a list of data sets that might look like what I saw down there, each of which will have a price tag. And so if you're a buyer and you are potentially interested in buying one of those data sets, you can pay the price and you will obtain it. And I argue that these marketplaces do not work very well for a couple of different reasons. The first is that pricing data is very hard. And I'm glad that Thibault just presented before me because he gave two of the key reasons for why that is true. Pricing data is hard. Sellers risk losing revenue if they set up a bad price. And I say that the buyers risk overpaying. Why does a buyer risk overpaying? Because maybe what the buyer is trying to do is trying to build a machine learning model, say, and believes that there's certain attribute on a data set that might help them predict the variable of interest. Now, the problem is when you get to the market and you see a data set that might be potentially relevant, you don't really know for sure if it'll be relevant. And so this is a challenge because now you risk paying for a data set that's not going to help you out. And of course, the seller is not interested in releasing the data ahead of time because, well, they want to monetize access to it. That pricing data is hard. Combinatorial power is what I believe Thibault referred as the value of data is contextual. I think it's sort of alternative ways of thinking about it. Non-rivalry, everyone could have access to data, at least in principle. And that is true because data is essentially free to replicate. So these are the kinds of scenarios that I would like to concentrate on today. And essentially, the goals that I have for the talk are, first, to present a stylized data market model. Then I'll tell you a little bit about what happens when you present that model to users, to actually real humans. How do they strategize? And then I'll be talking a little bit about some of the protection techniques that we've implemented to try to shield this market from those strategic buyers. So the market model is very, very simple. We have sellers on one side, here on the right-hand side, and we have buyers. So essentially, the timing, the way this is going to work is the sellers will upload some of their data to the market. Then there will be some buyers that will generate some demand, perhaps by telling the market what are the kinds of tasks that they want to solve. There will be the opportunity for what I call here the arbiter. That will be the market, the central platform that plays the role of the market. There will be an opportunity for them to perhaps combine data, apply any kind of transformation to data that's necessary to satisfy the buyer's needs. And part of that will also require pricing that data, right? So again, the buyer says, this is the data need that I have. The market will figure out if there is a way to satisfy that need based on the data that the sellers have uploaded. And in doing so, it will also try to come up with a price to extract that revenue from the buyer. And then finally, in step 5, there's the exchange, right? The data gets allocated to the buyer in exchange for the price. Great. So as I mentioned, the buyers will send queries of the style of, I want to augment this table, which is equivalent to say I have maybe a training data set. When I'm training my model on this training data set, I'm getting an accuracy of 0.6. I wonder if there's some data that someone in the world has that when combined with the data that I have would boost the accuracy of my model to 0.8. Because if that happens, well, I may be willing to pay for that difference in accuracy. And we can think of many other queries. Whatever the query is, they will all get abstracted into that bit that the buyer is submitting to the market. They'll say, for this improvement on this metric of interest for the task, I'm willing to pay this much money. Now, the requirements for this market are, I want to maximize revenue, and I want to do that because unless the market maximizes revenue, it will have no incentives to ask the sellers to put their data in that market, right? So I want to do some kind of revenue allocation for the sellers, which I'm not going to be talking about today, and that's why the goal will be for the market to maximize revenue. I say that there's an unknown value distribution, which what I mean by that is that the market cannot assume any distribution on the values that the buyers are going to have. And the reason for that is that data can be used for many different purposes. The market cannot know what those purposes are. In fact, the same buyer might be using the same data set for different purposes over time. So we just don't want to assume that we have any prior on what that valuation might be. And the last, which is one that I sort of links back to the idea that I was mentioning earlier, that I care about like actually building software that I can deploy. I care about everything working in low latency. Like everything has to be easy to implement so that I can deploy it efficiently. And I will be making some more connections about why that matters here. So how does the market work? So the arbiter is going to set a posting price. So that's going to be PT of D, which is the price of some data set at some time T. And then it's very simple. The buyers submit a bid. If the bid is higher than the posting price, they get the data allocated, and otherwise they won't. And so now you may ask, well, why this mechanism, right? Why am I already committing to making the market work that way? Well, first, this mechanism does not require knowing the buyer's value distribution. I just made a case for why I wanted to avoid assuming that. Most importantly, it's simple, and I know how to implement this fast and efficiently. And last, what is interesting is that it lets us set the price of D, of the data, based on the demand, based on the different bits that we are receiving from the buyers, which is ultimately what we want to do to avoid one of those problems that I mentioned that marketplaces today have, which is that you have to basically set the price based on your previous knowledge, but there's really not a principled way of doing so. So with that context, let me give you, maybe describe what is the utility for the buyer, and this will be important to then characterize how they will strategize in the market. So buyer I wants to obtain some data to maximize their utility. There's 3 terms in that equation, and they are all very simple, right? The first one is the allocation function. If the bid that the buyer submits is higher than the posting price, they will get the data. They will not get the data otherwise. They will have some private valuation. And again, this might match, for example, their understanding of how valuable it is to increase the accuracy of a model by 10%. So they will have the private valuation. And the private valuation, what is worth the data minus what they pay, that will be at the other component of the utility function. And then the last one is this deadline function. So what this means is that if the allocation happens before a given deadline, then the value will be determined by the other 2 terms. Otherwise, it will be 0. And so the idea of setting up this deadline is that many times we talk to people in organizations that tells us, look, I'm sure that someone in my organization will have the data that I need, but there's like 2,000 databases. I just don't know who is that person. I don't know how to access that data. It's going to make me go through IT and fill a ticket and all that. I may as well just source that data set outside if I can find it. But if it's going to take too long to get the data set from the external market, then they will still do the work internally, right? So that is sort of the intuition behind this deadline function. And you can think of the deadline function as I mentioned, right? Like a step function is 1 while the data gets allocated before the deadline and 0 otherwise. So let me just say real quick about these 2 parameters. For V of I, the valuation for the buyer, we assume for now that it's known. There are different things that we could do there, but we are going to assume that the buyer knows, that someone's done the work to figure out what is worth that 10% worth of, predicting better what's going to be the stock in a location facility, say. And the patient function could take other forms, right? It could diminish over time more smoothly than this step function that I described. I don't think that matters very much for the results and for the rest of the work. And this was sort of simple enough that helps us make progress. So that's why I'm going to stick to that one for now. So great. So now the piece that's missing is great. So now we have the buyers sending bits. We know how the market will allocate those. The question is, how do we design the function? How should the market consider those bits to set that posting price, taking into consideration that what we want to do as a market is to maximize revenue. Okay, that's kind of the goal here. And the challenge is, of course, that the buyers know that the posting price depends on the bits that they submit. And so they will be thinking, how can I game that market in a way that perhaps I can reduce the price and get it to maximize my utility? That's going to be the idea. So now at this point, what we ask is, how do buyers strategize? And in particular, we ask, how do they strategize in practice? So you could imagine how I could have taken that model before and try to analyze it mathematically and understand what are the set of actions that lead to the better utility for the buyers, and which of those are at odds with the goals that I have. And those would be the strategies that we want to avoid. And therefore, I would not have maybe proposed that model, but instead come up with a model that avoids those cases. Right? That would be a reasonable way of designing the mechanism. Here, however, I've already imposed what the mechanism is, and I want to understand how the buyers will react to it. Rasul?
So here you're assuming that the buyers do not communicate with each other to get access to the data, right?
That's correct, yes.
No externality among them.
That is correct. That is correct. I assume that they do not talk to each other, and there's no externality so far. And that's an interesting point. Like we can talk about like what would be the implications of that maybe later after I present the results. Are there any other questions here? So let me tell you very quickly how we measure this. We actually run a user study. We recruit participants. We tell them to play the role of a data buyer at a company, and I can give you details on how we do that to avoid the many threats that may appear otherwise. And then we tell them the utility that you gain is what your company values the data that you're trying to obtain minus the payment, right? Minus what you have to pay in the end. So this is a way of telling the buyers or telling the participants what's their valuation. We say your company wants to price this at most 500, say. Now the buyers do not know that the data set's price, right? They don't know the posting price, of course. They only know their private valuation. So they will be bidding in the range 0 to 2 multiplied by their valuation. That's what we allow them to do. So now we tell them, all right, so you can only bid once. We start with this experiment. And the company values the data to 500 and 1,500. Right? So now, if I were to ask you, what would you do as a rational buyer, if you will, is, well, you know that based on the mechanism that I just presented, what you bid is not what you pay. Right? You bid to try to win the allocation. If you win the allocation, you pay the posting price. So you would probably bid 500 in the first case and 1,500 in the second case, because it maximizes your chances of winning the allocation, and you will end up paying whatever the posting price is. Does anyone disagree with that? Okay. So this is what we actually observe in practice. If you look at the mean and the median, the 2 rows indicate the 500 and the 1,500. It is close to the 500 and 1,500, but it's not quite there, right? There's actually a standard deviation there that tells you that there were people who actually bid above and below. So I thought this was interesting because I said, well, they don't bid truthfully fully, but like we can say that this is near truthfully, right? Over a distribution of 50 users, I mean, they essentially got the idea of how the mechanism worked, and they were bidding roughly around what would be the truthful price. Now, I said earlier that one of the problems with data is that it has infinite supply. So there is no reason to let the buyers only bid once. The data is not going to disappear. It's not like a car that if I sell it to you, I cannot sell it to someone else. Data, I could sell it to everyone at the same time. It's infinite supply. And furthermore, buyers have a deadline, as I mentioned earlier, a time by which they want to get the allocation. And so they could potentially figure out in what sequence of bids can I send to the market to drive the price down to then optimize my utility. They could ask that question. And so we hypothesize that there are two strategies that they will follow. And what we do is we measure what happens in practice. Do they actually follow those strategies or not? So let me talk about the first strategy real first, right? Like, it's very simple. What I'm saying is that if a buyer can bid at time T1 and T2, a strategy would be to bid very low, like lower than the valuation at T1, hoping that the posting price will be adapted downwards with the intention of them bidding truthfully later on time to win the allocation. But now I'm winning the allocation with a higher utility because the price went down, right? So we ask, is this really what buyers will do in practice or not? Again, we tell them that the company sets the value to 2,000. And here I'm showing you in the x-axis there are 3 hours. And we tell them that they can bid once per hour. And then I'm going to show you the amount of what they bid on the y-axis, right? So let's concentrate on this point first. This is the 3rd hour. This is the last opportunity they have to bid. And when we look at that point, and I'm showing here the distribution of bids, right, across the 50 participants, 25th, 50th, and 75th percentile. When we look at those points close to the 3rd hour, they are what I called earlier near truthfully. They are close to the 2,000. That's what you should do if you really want to win, right? But if you look at the trend, they actually were trying to do something there. They were trying to really engage in some kind of strategy, right? They were bidding lower earlier, and we can see that upward trend. So they do use multiple opportunities that they have to strategize. We observe that this is indeed what they do. We could also argue that this is not the best strategy. If you want to strategize, that's not the best strategy. You may as well just bid as low as you can to try to really price it downward, and then the highest, right? But that's the strategy that we observe in practice. So great. So we put this mechanism out there. We measure what are the kinds of strategies that buyers engage in. And now what we ask is, how can we protect the mechanism against that behavior that we've observed? So remember that one of the key problems is that they're going to underbid first to drive the price down. How do we protect against that? So the idea of this epoch seal mechanism is very simple. Instead of adapting the posting price every bid that we receive, we are going to adapt it every epoch. And an epoch is just going to be a partition of time, right? So rather than adapting every bid, I will adapt every set of bits, the set of bits that fit into a given epoch. So now that function A, which is the function that will take the collection of bits and come up with the posting price, I mean, you can see how if we make it an average or a median, that's really not going to help us very much because, of course, now I can still bid low, and that's still going to move both the average and the median down. So the key idea then is, how do we design A so that it's hard to game? And it's hard to game if a single bit's influence is not very significant in the final price, in the posting price. And if it is not clear for the buyer, and this is the most important piece, how to drive the price in the desired direction. If I were to say average or median, it's still very clear. You bid low, that's going to do the job. So this is what we do. We choose the posting price based on the standard optimal way of choosing the revenue maximizing posting price offline. And what is interesting about this, I mean, is everyone familiar with that expression? I believe so. Essentially, the idea is if we have this sequence of bids, I sort them. I give each of them a position, 1, 2, 3, 4, 5, as you see. And then all I do is I'm multiplying the position by the bid. Because I know that, for example, if I set the price to, say, 4, then there are going to be 1, 2, 3, 4, 5 people who will get allocated, and they will all pay 4. So I'm going to get a revenue of 20. So I just check what would be the revenue that I would get given the different bid, if I were to set each of these prices, and I pick the one that would give me the maximum revenue. So what's interesting about this very simple mechanism is that, well, first of all, it's very easy for me to implement, again. But crucially, this is what the buyer would need to do to game it. They would need to basically solve this optimization problem. They want to find some bid that basically makes the revenue be higher with the bid than without the bid. So otherwise, the market will not incorporate it. And at the same time, the price has to be lower. Or otherwise, they are not winning anything, really. They are not gaming it. And this is very hard for the buyer because the buyer doesn't even know what are the other bits. The buyer, as a buyer, I don't know what are the other bits that other people sent. So that's just basically impossible for me to decide, right? And I think it's a very sort of simple, intuitive idea. It also introduces this trade-off, right? Like the larger the epoch, the larger the protection, because the more information the buyer intuitively would need to know to solve that optimization problem, but also the lower the revenue, right? And I can say a little bit more about this if people are interested in how exactly this affects in practice the bits. Yes?
So Amazon has spot pricing for EC2, right?
Yep.
So what do they do?
So this is a great question. I have a hint of what they used to do 4 or 5 years ago. I don't know what they do now. But my sense back then is that they were only offering as spot instances the excess supply that they had. And so they had already paid upfront for those resources anyway. So the price that those resources would cost them had been determined in the past. And so I don't know exactly how that's changed. But I like that question because I think that there could be some kind of connection between these kinds of mechanisms and what they might be doing. Yeah. And in fact, not just for spot instances, but for Lambda instances as well. It's a good question.
I guess one difference is that here there is no capacity constraint or anything.
That is
Free, so I guess the strategy might be different.
That is exactly right. That is exactly right. Why they have clearly a set of resources that they need to account for. Yeah. So that might be what changes a little bit the problem. But good. So does this epoch shield make sense? Okay. So we are just tempering the effect of any one bit, right? Now, remember that the buyers were strategizing over time. I said that this might not have been the best strategy, but they were doing this nevertheless. So how do we protect against that? So this is what we do. The strategy, again, what happens here is that we have the timeline. We split the time into periods. We call period intuitively to the points of time at which a buyer can actually submit a bid. And they have as many periods to bid as periods are there before their deadline. And remember that the deadline is private information to the buyer. The market doesn't know that. And so what we've observed is that the buyers will design that sequence of strategic bids, and that's what we want to protect against. So here's the idea. It's very simple. If a buyer bids and loses, we'll make them wait. And we'll make them wait as long as we need to so that they can only bid once more. Because we know that when they can only bid once more, they bid near truthfully. The challenge is that, of course, we don't know what's the buyer's deadline. As I mentioned, like each buyer can have a different deadline. They may actually not know in practice what the number is. They just say, well, I'm tired, so I'm just going to do the work. But there is a deadline. So how do we choose that waiting period? That's WI. That's kind of the key challenge here. And it's a challenge because if we make honest loser buyers, that is people who were not trying to strategize, but nevertheless they lost the allocation, if we make them wait, we might be harming their utility, right? Because now we're not giving them a chance of actually getting the data allocated within the deadline. Does this constraint make sense? It's like I want to make wait those that are strategizing, but not those that are not strategizing. And the problem is that I can't really tell which one's which. We know, though, that any wait period that's more than 0, any positive wait period, will disincentivize strategic buyers. At least we hypothesize that that is the case, and we will be measuring in a bit. So the idea to set this up is, or the intuition at least for how it works is, we will calculate the minimum time at which the bid that lost would have become competitive. So competitive simply means that the bid would have won given the posting price. So I want to know this bid that they submitted, it's lost the allocation right now. When in the future would have been competitive? When is the earliest that it could have been competitive? And the earliest that it could have been competitive, that's going to become the wait period. Okay, so now the reason why we can compute that price is because the arbiter knows the function that is running on the sequence of bits to compute the posting price. It knows the past bids, and it knows the losing bid. So we can compute the most conservative, closer range of time by which that bid would have become competitive. Another way of saying it, or phrasing the same thing, is the W, the wait period, is set up so that the buyer would not have been able to win the allocation earlier, no matter if the original losing bid was truthful or not, which is essentially what kind of matches the intuition that we have, right? Our constraint that we have. Does this make sense? So we implement that. Now I'm showing you again the same graph as before. This is what happens. Now I will introduce the key. I was using NW to refer to non-wait. So this is, we tell them that they will have to wait, but we don't tell them anything else about we don't tell them that they have to wait in this case. So now what we're going to do is we're going to include the intervention. We introduce this time seal technique, and we again measure the effect. So now we can tell the NW is again non-weight. The W is the weight when there's wait period introduced. So if we look at, say, for example, the 75th percentile, for non-weight, this is the dotted grid line. So this was sort of the behavior. Now you can see when we make them wait is that everything goes upwards, right? So again, like at the end, when they only have one chance, they all beat near truthfully anyway. But in the previous cases, in 1 and 2, all of the bits went up. Now you could still argue, well, but it's still kind of a weird behavior because you would want to beat the 2000 anyway from the beginning. Well, that's true, but that's not what people did. And the mechanism somehow helps to get those bits up, right? And therefore, the revenue will be higher. That's kind of the whole point. Does that make sense? Yeah.
So the mechanism is that so when the hits, they are forced to wait for a certain amount of time.
If they lose. So we tell them, if you lose, you will have to wait, and we don't tell you how long.
You don't tell me how long.
Right. So you know, as a buyer, all what you know is that you may need to wait.
Okay.
If you lost the allocation, but you don't know for how long.
But it's different for different users. I mean, it
Yes.
depends when you made your last bid.
Correct. Exactly. It depends on when you made the last bid, what was the posting price, and also the value of the bid.
Okay.
That's exactly right. But we don't want to tell them for how long, because that would be kind of leaking the price. If they are smart, they can. Right? But that's exactly the mechanism, yes. So just the fear of having to wait makes them push the bids up. That's the idea. Yeah. It's a good question. So we could do that, right? We actually can enforce that. I think it would be limiting from the market perspective, because the same data set could be used for many different tasks. And if they happen to, say, a zip code data set, right? I need to access zip codes for computing the causal inference on this task over here, and also to figure out, how many different counties are in the US. I don't know. So if I only let you bid once, and you bid for the causal inference task, I'm basically prohibiting you from accessing that data set ever again. Or I will need to set up some time. It's unclear exactly how it would work out. So while intuitively you are absolutely right, that's essentially what we're actually trying to do here. We're trying to go in the direction of letting them only bid once if they lost, right? Yet, we don't want to make that constraint from the beginning, because otherwise it would mean that they would not be able to be using the same data set for different tasks over time. Does that make sense? Right, I guess the question, if I were to prevent you from bidding again after you lost, right? Then that means that basically I've cut your access to the market, right? Forever. That would be the way to. For that data set, yeah, but keep in mind that the data set could be a combination of data sets. So any data that's been touched by this data set, you can't touch anymore, right? Again, I'm not saying this is not a solution. I'm saying it could be done. It just seems very limiting from the perspective of implementing the market, because you will need to keep track of what are all the data sets that are banned for each of these individuals, and banned for how long, really, right? Because we probably wouldn't want to do it forever. We probably would want to put some kind of limit, and then it becomes very hard to answer how do you choose that value. But I mean, the intuition is, this is what the waiting period is doing. It's trying to actually go in the direction of, you will only be able to bid once more. So how do we do that? How do we get there? So the intuition is correct. I think there was another question. Yeah, Thibault? Correct, great. You don't know the future bits, so you need to simulate the sequence of future bits. So let me give you more information. So we have an algorithm that is actually computing the price. So in this case, it's going to be a multiplicative weights. That's what we choose. So we have the experts are each of the posting prices, each of which has a weight. You send a bid and you lose. And now I say, what would have been the smallest bid that you could have sent, which would correspond to the bid that would change the weights of the multiplicative weights of the experts the most? And I say, how many of these would I need to receive in the future for the price to go as fast as possible down, up to the point where your bid, the one that lost, would become competitive? I can compute that, right? That's deterministic. And then the question is, well, how many bids am I accepting per unit of time? And how many periods does that correspond to? Correct. It's worst case actually for the buyer, right? Because if the incoming bids are not the lowest, which are likely not going to be the lowest, then the time will be actually longer in the future. But we want to be conservative to ensure that we are not harming honest loser buyers. That's the idea. So that's a great question, right? So those are the kinds of things that we actually know how to enforce at the technical level, right? Like it could be like I actually request an identity from you, and it has to have a cryptographically signed ID, for example. What is a little bit harder is if you were to want to collude with someone else. That we don't know. We don't have an answer for. But in terms of ensuring that you are who you say you are, that we can use cryptographic techniques at the system implementation level to ensure that the bit comes from you and not someone else. You say if you share the data among you, yeah. Oh yeah, you create your own black market behind the scenes. So this is a potential problem. I can tell you what the evidence that we know exists. So if you look at the data broker industry in the US, it was like $60 billion in 2015 when the FTC was commissioned to write that report. The people in their own data brokers, they looked into, do the black markets exist? Is it true that people buy a data set from our organization and then they put it on a market where everyone can share it, essentially, right? Or sell it for lower, and they don't seem too concerned about that yet, which doesn't mean that it's not an issue, because as you said, like if you know that there's a group of people who are interested in a given data set, there's no reason not to do that, because again, data is free, replicable, and it's non-rival. If you are interested in offline, I can tell you what are some of the techniques that we are working on, like at the systems level, to try to prevent that. It's kind of independent from this model, though. Here, you're absolutely right. If I buy the data set, then I can make it available to anyone else who I know might want to access it. And as I said, this is a problem that any data market suffers from, at least in principle. It's a good point. I want to tell you give you one other result, empirical result that I thought was interesting, and then I'll sort of start summarizing, okay? So I mentioned how we put this mechanism in the wild. We measure how people interacted with it, and I've told you about two protection techniques so far, Epoch and Time Shield, which are designed to avoid or to temper the impact of any one single bit, and also to try to prevent people from strategizing over time. So let me tell you about one other shield that we had to implement after some behavior that we observed in the wild. So imagine this. Imagine that before bidding, the participant learns that the arbiter, the market, is setting price based on the past bids. They don't know exactly how, maybe, but they know that bids are set that way. And they would know that, right? In any market, we would tell them essentially how the market works. So that's not very surprising. Let's also assume that the participants get access to the latest price set by the arbiter. So there's a particular data set that they're interested in, and they know that this data set was sold by 50 1 week ago. So the hypothesis that we have is if they are thinking of bidding for that data set, some price, and we tell them what was the last price, and the last price happens to be lower than what they were thinking of bidding, they will lower their bid. That's the hypothesis that we make. Now, again, because this is a posting price mechanism, doing that like this, engaging in this strategy makes no sense, right? Because you're just strictly reducing your chances of winning the allocation, because you pay the posting price anyway. So it doesn't really make sense to do that. And we also speculate that if we were to add some randomness in how we set up the price, basically trying to weaken the link between the way the posting price is choosing the bid and the bid and the allocation decision, that also will make buyers be a little bit more careful in how they do that, right? These are the two things that we speculate on. So I'm kind of curious, what do people think would happen? Like if, say that the company says the data set costs, or we value the data set at 500, and you are a rational agent, you're thinking, well, I'll bid 500. But now I tell you, this same data set got sold by 200 yesterday. You wouldn't change your bid, right? You would just keep the 500, because then that ensures that you win, and then you will pay whatever is the posting price today. So those are the two questions that we ask. This is what we observe. So first, when I say no leak, this yellow line, this is a company setting the value at 500, by the way. And this is a histogram, the bid range and the number of people who bid that range, right? So the yellow corresponds to the near truthful bids that I mentioned earlier. So here they are just trying to obtain a data set that is valued at 500, and they're just bidding near truthfully, right? If we leak a price that is lower than 500, that is this past, the bids drop, right? And let's be clear, these are participants who have gone through a tutorial. Well, first of all, these are participants who have at least a master's degree, who work in the finance or computer science sector, who've gone through a pre-screening interview for running this study, where they have to basically understand a second price auction and the fact that allocation and payments are two different things. So they understand all those things because they pass a quiz to run the study, and yet when we tell them that those are past bids, they drop their bids. Does it make sense that are we all on the same page that this behavior doesn't make sense? Okay, so this is what we observed. And I replicated this user study twice because I couldn't believe it, right? If we add some randomness to the prices and we tell them about it, then they intuitively think, oh, okay, hold on a second. So then it's not longer true that the posting price is only set based on my bids. There's also some factor that I don't control. Therefore, their bids move up again. Now, notice that they move up, they don't really, they're not equivalent to the no leak. But it kind of, fixes that behavior a little bit. Does that result make sense? It was sort of surprising for us when we saw it. So there's something to be said about strategy of Libu's strategy proofness and such, because it really is. I mean, it's not a very difficult mechanism, and yet it creates this kind of confusion, right? When you put it in front of real participants. Good. So in the paper we have an algorithm that implements those three techniques. It's based on multiplicative weights, as I was mentioning earlier. We also have a discussion on how differential privacy could be leveraged to achieve some of the same goals. In practice, it's a lot harder to make it work than multiplicative weights. So we went for multiplicative weights, which we all know very well, and it just works fine. And there are some other extensions in terms of what happens if the buyer would not know their private valuation and so on and so forth. So there were lots of different questions that we asked here. Many of these I've already sort of answered throughout the talk. These are most of them the ones that are directly related to the empirical aspect of the work. There are a couple of other questions that are more related to the specific mechanisms that we implemented. Like Epoch Seal is adding this epoch, but as I mentioned, it increases the protection of the market, but it reduces the revenue. So we ask, how does that affect the performance? And uncertainty seal, I mean, of course, if you add randomness to the price, you're also breaking that tie. It helps to avoid some of the non-rational or boundedly rational behavior that we saw, but it also affects performance. And so here we ask by how much. And we basically run two experiments. The first one, so we create time series. We use an autoregressive model in this case. Each point in the time series represents a buyer and a bid. We create 100 time series, each with 250 points. So I'm going to be showing you distributions. So in this plot, what we have is we have the percentage of strategic participants in the x-axis. So it increases from the left to the right. So here, everyone is truthful. Here, no one is. And then we have the normalized revenue. It's normalized because we don't really care about the specific dollar amount, but rather, within all the possible revenue, where are we? And then what we are showing is different epoch sizes. Remember, these are the windows by which we obtain those bids, right? So the message here is very simple. If I set the epoch to 1, let's look at the truthful scenario first. Everyone is bidding truthfully here. Epoch to 1 leads to higher revenue than, say, epoch equals 16, right? Like if you compare the leftmost box plot with the rightmost, you see a difference there. Now, that loss in revenue is justified because as the number of participants increases, you can see how the revenue for the larger epoch still remains the same while the others start dropping, right? So it's very intuitive, really very intuitive result, I think. But it kind of shows this point that even though we are introducing a trade-off, we need it if there are strategic participants in the market. And because from the user study we did indeed observe that there are strategic participants, it seems like a well-justified intervention on the algorithm. So, and here very quickly, uncertainty seal. What happens if we add a random noise, right, to the prices, to the posting price? So we have several variants. We have multiplicative weights is the black box. That's what we actually run. And multiplicative weights, as you know, when you pick the next expert, you check it based on the distribution of experts, right? So there is inherently some randomness on which expert is going to be chosen. For multiplicative weights max, we choose always the best expert, eagerly. There's no randomness. That leads to higher revenue. But remember that it would be subject to that problem that I just described earlier, which is that if people learn about some past bid, they will move their bids down. So multiplicative weights will be the intervention that we do to avoid that behavior. So it reduces the revenue a little bit, but it's still fairly competitive with multiplicative weights max. And then the other two baselines are essentially, what about other random ad hoc techniques to do that? And those, of course, really do not work very well, and they reduce the price, right? So in other words, these techniques that we implemented to try to protect the market do have an effect on the revenue. They impact the revenue negatively, but their negative impact is less than the positive impact in avoiding the strategic buyers. Okay, so let me stop. Let me just take 30 seconds. So I said earlier that I'm very interested in studying data markets. I'm very interested in looking at almost every environment where agents exchange data as a data market, because that lens allows me to ask questions about what's really the role of the agents there, right? I think there are many such data markets that have been discussed in these last 2 days. I think it's really fascinating. The state of affairs today is that there are many data markets that really do not perform very well. These marketplaces might be one example of them. There are data markets that make us harm. And there are other data markets that I think would be fairly beneficial, but do not exist because we haven't been able to engineer them yet. My goal is to build deployable software. That's what I'm really interested in. Studying mechanisms, studying models. How do we, narrow down the large design space first, and then what are the right set of things to implement? And translate models so they work in the wild is one of the things that I've been very excited about doing for the last couple of years. And in terms of understanding how data and models complement each other, I think that's a relevant topic, I think, to many of the talks that we've heard over the last 2 days, and maybe one of the attempts that we did in the work that I presented today. So I propose a model that reflects some data markets. I set a mechanism that I know I can implement efficiently. I studied how that mechanism would be attacked in the wild with the user study. And then I've told you a little bit about these protection techniques and how they affect both the behavior from strategic participants and what's their impact on the revenue of the market. And many of the decisions on what interventions to do, what techniques to implement were driven by data. Like, even though I had some hypotheses, we really did measure things and said, all right, so it seems that they do really are strategizing. What can we do about that? So I'll stop there, and I'll be happy to take any questions and discuss anything else offline that people are interested in. Thank you.
How would the behavior of buyers change if you allow them to be more? And how would it affect the overall revenue?
So that's a good question. So even though I saw results where they could only beat twice because there were like 3 hours, actually we ran experiments with many more times, right? And the trends are basically the same. Like, we changed the price, like the value that the company set for the data set. We changed the number of times that they could bid. The trends are the same. So they will look at how many times can I bid, and they will try to figure out, all right, so how can I bid lower and keep increasing until I drive the price down to then increase my utility.
How about the revenue?
Correct. Like, if we were not to protect the market, it'll go down, right? Because as we've seen, they really do bid lower. And so that's going to be affecting the posting price, which is going to be lower than it could be, right, based on the real valuation. That's what justifies trying to find a technique that seals the market from that behavior, that makes them try and bid higher, right? And so we did measure that the effect was such. They did bid higher. Of course, they still bid lower than the truth valuation. So there is revenue that is lost, for sure.
So do you know of markets which behave slightly differently in the sense of the arbiter who's selling the data, he doesn't release the entire data set. He just releases a little bit that you can experiment. Essentially, I'm trying to take an information design viewpoint.
Right.
Where then, that way the people buying the data don't know the value of the data as well, but they can experiment. They have some ML code. And using that, then you construct the market afterwards for the bids. And then it seems more logical. It seems a better setup. I don't know. Have you seen markets of that kind, or
Yes.
Are they going that way or not?
100%. So if you look at the Scale AI and all these different set of startups that are essentially trying to collect data from people and give it to the crowd for labeling, they work very similar to what you just described. We are working in one such market. Now, and the problem is what kinds of signals, like the problem here is that in the information design setup, the signal is costly, right? Because any signal that I give you about the data set that I have is actually giving you information about the data. So if you misreport what you want to do with the data set, it could be that the signal that I'm giving you is all what you need, and then you just walk away, right? That's a challenge. But you are right. This is a super interesting market, one that we are working on. I would add, though, that there are many cases, and if you look at Axiom, the kinds of data brokers that I was mentioning earlier, people actually want to buy the data set. They want to actually have the full data set. They are not OK with telling you actually what is even the task that they are trying to solve. So that happens sometimes. There is privacy on the task side. And so, it may feel like an easier market to design. I think it's a super interesting design for things like supervised machine learning specifically, where we can evaluate the quality of a model without knowing anything about the underlying data. At least sometimes we can do that. But the message is that there are other markets where you really want to access the data in the end. And so the question is, how do we do that, right? But it's a great point on the design space of markets is huge, right? And depending on the tasks that you have, maybe we need different designs and different models for sure. After the leakage?
Yeah.
So you're saying we tell the buyers this was the price at which this data set was sold in the past, and then you have n opportunities to bid. Is that the question?
Yeah.
So let me think if we did that. I don't know that we did run that experiment. Because we kind of thought about this as two different behaviors, each of which would make the buyer act in a different way. So for example, having multiple opportunities means that they will just be trying to create the sequence of bits that will drive the price down. Mm-hmm. They will already do that, even if they don't know what the past price for the data set was. And then we wanted to say, what if they could not bid several times, but we gave them a past bid, right? And then we observed the same. I mean, I wonder if we were to give them the two pieces of information, would it change? It's a good question. We didn't run that experiment.
Yeah, unless I find a marketplace where I can actually get the data for that price, I won't bid lesser, right? I mean,
unless you find a marketplace where you can find the data for that price, you wouldn't what?
I won't lower my bid, right?
You wouldn't lower your bid, you say?
Yeah.
Oh, so you are thinking of someone who might be actually playing with other markets at the same time. Mm-hmm. That's so interesting. Yeah, no, we haven't thought about that. But that's kind of, it goes back to the kind of competition that could be created if the data could be sourced from different places, which goes back to the question that we had earlier on, what if I buy the data and then I sell it myself, right? That's a good question, yeah. No, we didn't study that.
Thank you.